Okay, so this lecture will be lecture 3.9. 3.9 from your text, 3.9 in the videos, lecture 3, part 9. And in this lecture, we're going to talk about applications of derivatives, namely related rates. So this is a rather challenging section of the text. So related rates are essentially word problems. And the solution to these word problems will be having to involve using the chain rule for differentiation to get the answer. So with related rate problems, they go something like this. Let me pull up a flow chart kind of thing. Let's see if it'll let me. And this is in the text as well. But the procedure, or the sequence of steps to think about when you solve a related rate problem, is the following. All right, so what you have to do is, like with any word problem, you have to read it carefully and keep a balanced perspective on the quantities that are described in the word problem and the relationship between quantities in the problem. So what you have to do to successfully solve a related problem oftentimes is to draw a diagram of the dynamic that's going on in a problem, because with related rates you're going to have something changing, usually with time, such as the motion of a projectile along a path, for instance. So you're going to encounter things, or say the water level rising in a tank, the water level rising with respect to time. So you may be asked to find out how fast the water level in a tank is rising. That's a typical problem. So in order to do that, you may have to sketch a picture of the tank, and you may have to sketch water flowing into the tank and water flowing out of a tank, or something like that. So this would be your usage of notation and symbology to annotate a diagram which shows some phenomena changing with respect to time. And then, so a rate, is a change in some quantity with respect to time. So that's a derivative, a derivative with respect to time. And so this is particularly important to you guys going in engineering. So you need to develop a facility for writing something in terms of a derivative. And then of course, in the problem, I'm on step 5 now. In the problem, it may be the case that several different quantities are changing with respect to time. In other words, you could have, say, something growing in the y direction and something decreasing in the x direction, but they were somehow related. So you have to express a change in y with respect to time in terms of the change in x with respect to time. And I'll show you an example of how that works. And the reason why you want to do this is so that in step 5, what's inherent in step 5 is you'll have an equation with more than one variable. That may invariably arise as you model the phenomena going on in the word problem. And so what you want to do is you want to eliminate the excess of variables. So essentially reduce the problem down to where you have one equation and one unknown, which lends itself either to the solution of that differential equation or perhaps the solution to an algebraic equation, which would be ideal. Now, like I said, the calculations of derivatives in these word problems will involve having to use the chain rule for differentiation, and I'll show you that. So please, if you're not comfortable with the chain rule now, this would be a great time to become very proficient in its usage. And then, of course, 7 is related to 5. Well, you basically, once you solve for one of the variables from the equation from step 5, then you take that solution and you use it to calculate the value of the other variable or remaining variables through some sort of substitution regimen. So the best way to deal with this is simply to work some problems. Now I'll work a few from section 3.10 of the text. So I'll start off with, say, oh, by the way, I should mention that on the class website, I do have quite a few of the even number problems from section 3.9 posted. And if you have the solution manual, of course, you'll have access to the odd number problems in the development of their solutions. So potentially you have upwards of 40 or 50 examples of word problems that deal with related rates. So you have really quite a bit of material and a lot of problems to study. And I encourage you to look at some of the ones that I can't get around to lecturing on, so it's very much worth your while. And you'll notice as you work through a lot of these problems that the techniques are essentially the same. There's a pattern of solution that appears consistent throughout the solutions of all these problems. And then if you can discover that pattern, then of course you're basically achieved a point or a milestone where you're pretty good at solving related rate problems, and I hope you guys get there. So next page, let's solve section 3.10, problem number, let's see what that one would be. This is, I'm sorry, section 3.9. How about problem number 44? It's actually kind of an interesting problem. So number 44. So we have two people start walking from the same point, right? So two people start walking away from each other at the same point. Okay, so the two guys standing next to each other, and then they start walking away from each other. One walks east at 3 miles per hour. Okay, and let's see what else. And the other walks northeast at 2 miles per hour. Okay, and so the question is, how fast is the distance between the people changing after 15 minutes? So here we go. So how fast is the distance between the people changing after 15 minutes? Okay, so at the outset, you'll notice that the time in this problem is expressed in 2 units. We have the distance traveled with respect to time is in miles per hour, and then we want to know the change in distance between the two guys after 15 minutes. So what I would suggest is convert the minutes into hours, okay? Because when you do that, you'll have smaller numbers to work with. So kind of I think most of us are accustomed to doing that. So what you need to do is you need to draw a picture of the dynamic of the problem, what I call the dynamic. So let's do that. So we say the two guys start at the same spot, okay? And what you might want to do is say overlay a coordinate system, a rectangular coordinate system, okay? And the origin is where the two guys start walking. Okay, so initially they're together walking. Now, direction east, of course, is the positive x-axis direction. So one guy walks east at 3 miles per hour. Okay, so he walks in the x direction at 3 miles per hour. And the other guy walks northeast. So northeast would be this direction. Okay, this would be the northeast direction. Okay, so the angle between the two guys as they separate is 45 degrees. All right, so we can get that information. And by the way, well, no, I'll keep going. Okay, so the distance between the two guys at any point in time is this distance that I've shown in a red. So that's the distance. The distance is the shortest, the shortest distance between the two guys would be this red. And so we have this distance. And let me use an uppercase T, D, so as not to confuse it with the differential operator. So we'll that's the distance, all right? So what we want to find is the change in the distance between the two guys with respect to time at t equals 15 minutes, which is a quarter of an hour. All right? So you can see that d does change with time as the guys get as the guys walk farther and farther in their respective directions, the distance between them is changing. You can see that, right? At each time, you have these distances. So what is the change in this distance? This distance is getting bigger and bigger as time goes forward. All right, so how do we calculate what that is? So that's one of the strategies. The first thing we want to know is, right here, how fast is the distance between the people changing? So how fast? How fast is the rate of change of distance with respect to time? So you need to identify what your output of your problem is going to be initially. Okay, so we have this. Now, okay, so now the next thing we want to do is we want to calculate what d is as a function of time. So find a formula for d. And to be more precise, find a formula for d as a function of time. Okay, so what we've got here, so the way I would proceed is, all right, the distance, the guy walking in the east direction, okay, so we call this distance x. Okay, so we call that distance x. So x is distance traversed going east. So he walks X miles going east. He or she walks X miles going east. Okay, and now we'll let, say, Y be the distance traversed going northeast. Okay, so you see how we parameterized the system now? We've got three variables now that have emerged in the solution to this problem. So Y is the distance traversed going northeast. Not to be confused with the y-axis, okay? Y is a distance now. Okay, so this y is not the same as the y coordinate of a point. It's just the distance, as I've got labeled here. Now, so let's let z, let me give you another variable. Let z equal the distance. Instead of this uppercase D, why don't we replace D? We'll just let z equal to D. Okay, just so we have x, y, and z. Okay, for symbolic sake. So let z, which equals D, equal to the instantaneous distance between the two people. Okay, all right. So now, what is z? Okay, so what is z in terms of x and y? All right, it turns out that z, which is this distance right here, the instantaneous distance, we can use the law of cosines. So by the law of cosines, which I'll give you, okay, now bear in mind that x, y, and z are all functions of time because they do change with time, right? So we have the distance separating the two people is equal to the distance the eastbound person traverses. Okay, so that would be z squared. Z squared is equal to x squared plus y squared, the distance the northeastbound person traverses, minus 2 times x of t times y of t times the cosine of the angle between the two trajectories, which is 45 degrees. So by trajectory, the guy heading northeast is the northeast trajectory and the eastward trajectory. Those two trajectories are separated by 45-degree angles. Okay, so now, yeah, so far so good. And so now what we want is the change in d with respect to time. And so d of t, I've decided to recast as z of t. So just to be consistent with the pattern of using x and y. So now, what is, okay, so we want the change in z, so we want the change in z with respect to time. That's the answer to our problem. Okay, so we go ahead and proceed to use the differentiate both sides of this equation with respect to time. So we use the power rule for differentiation. So this would be 2 times the distance function times, now we have to use the chain rule because z is a function of time. So we have to take the formula for z with respect to t. Okay, and so this is the quantity we want. So 2 z of t times change in z with respect to time, and then we differentiate each of the terms. So that would be 2x times the change in x with respect to time plus 2y times the change in y with respect to time, okay, minus, so now we have to use the product rule for differentiation. So that would be, let's see here, minus 2, well, 2 cosine theta is your constant since theta is not changing with respect to time. 2 cosine theta times x times the change in y with respect to time, okay, plus the change in x with respect to time times y. Okay, we have to use the product rule for differentiation. Okay, and so cosine of theta is cosine of 45 degrees, which is 1 over the square root of 2. Okay, so we know that from trigonometry. So let's see, can we do anything else? Okay, so we can divide both sides of the equation by 2, and so we have z of t times dz over dt is equal to x times dx over dt plus y times dy over dt minus 1 over the square root of 2 times x times this quantity, x times the change in y with respect to t plus y times the change in x with respect to t. Okay, so let's see how we can proceed to solve for dz over dt. So we know the change in x with respect to time. Okay, we know that the guy is walking at a constant rate, and his change in position with respect to time was given as 3 miles per hour. So we can substitute in 3 miles per hour for this. So this is 3, and we know that the change in y with respect to t is 2. That's just, you know, the change in position with respect to time is your velocity, your time rate of change of position. And so we can put 2 here, and we can put 3 here. Okay. So now, what is z of t? So if the two guys walk for 1/4 of an hour, okay, so after, we can look at it from this perspective, we need to solve next for what is z of t? What would be a reasonable value for z of t? So after 1/4 of an hour, 15 minutes, okay? So after, which was our targeted time for the problem, right? 15 minutes, there's your 15 minutes right there. So after, yeah, 1/4 of an hour, our x value would equal to what? What would our distance traversed? X would equal to rate times time. And then the rate is 3 times 1/4. So the guy walking in the east direction will have traversed 3/4 of a mile. Okay, so we can put 3/4 in for x. All right. And let's see what else. And then after 1/4 of an hour, the guy walking in the y direction will have traversed, not y on the coordinate axis, but in the northeast direction, would equal to 2 times 1/4 of an hour, which is equal to, what? 1/2 mile. Okay, so we can plug in a half for y. Okay, and let's see, x is equal to 3/4, right? And y is equal to a half. So that means the only thing left would be to solve for z of t. And so after 1/4 of an hour, we want to know this. What is the distance separating the two guys after 1/4 of an hour? Okay, and so that would be, by the law of cosines, that would be x 1/4 squared plus y at t equals 1/4 squared minus 2 times the cosine of 45 degrees times x at 1/4 times y at 1/4. Okay, so that would be your z at 1/4. Okay, so solving for this, this would equal to let's see here, x squared at 1/4 would be 9/16, right? So it would be 9/16. Y squared at 1/4 would be a 4th. Okay, and then minus 2 over the square root of 2 times 3/4 times a half. Okay, so can we get a number for z at 1/4? So that would equal to 9/16 plus 4/16 minus 2 on the square root of 2 divided by 2 times 3/8. So that would equal to 13 minus 6 on the square root of 2 divided by, oh, by the way, that would be z squared. I forgot a squared. That would be z squared. Okay. 13 on the square root of 2 divided by 16 is z squared. And so z at 1/4 is equal to whatever this is, the square root of 13 minus 6 on the square root of 2, all of that divided by 4. Okay, so that's after 15 minutes, that would be the distance separating the two guys. So let's call this, we'll call this alpha. So alpha is some number. So now we go back and we say, okay, so we put an alpha in there. And now you can see that all we have to do is divide both sides of this equation by alpha. So the right-hand side is resolved to a number. And we can isolate dz over dt and divide both sides by alpha, which is this number. And then what you'll find out is if you use your calculator, the change in z with respect to time is equal to 2.125 miles per hour. So every hour that passes, these two guys will be separated by 2.125 miles. Okay, more. Okay, so after 1 hour, they're separated by 2.125 miles. After 2 hours, they're separated by 5.25 miles, and so forth. Okay, so I hope you gather the strategy for solving this problem. We had two variables. We had enough information where we could assign numbers to the variables because we were given two rates, and so forth. All right, so, all right, okay. What else can we work on? Quite a few word problems here. It's getting close to class time. Okay, let me see. 23. So let's talk about problem number 23. Next page in the text, from the text. So I'm going to go ahead and paste it into the whiteboard session here. So this is a case where water leaking out of a tank. Water is both flowing into a tank and leaking out of a tank. So let me show you here. So I'll paste it here. Okay, so in number 23, we have water is leaking out of an inverted conical tank. So first things first, I drew a picture, a sketch of an inverted conical tank. So you have to draw a picture of a cone. It's a right circular cone, and water is gushing out at 10,000 cubic centimeters per minute. Okay, so you have an outflow. Okay, so you've got an outflow, right? And at the same time, you've got an inflow of water. It's being pumped into the tank at a constant rate. So I guess we're not given that inflow. Okay, and so the tank has a height of 6 meters. Okay, so now we have a mixed unit situation. We have centimeters, cubic centimeters, and meters. And the diameter of the top is 4 meters. So that means the radius of this top section right here is 2 meters. Okay, so we have just about all the properties of the inverted conical tank. So, okay, so here we go. So the water level is rising. Okay, so the water level is rising at a rate of 20 centimeters per minute. So that means the amount of water that you're pumping in is overwhelming the amount of water that's draining out. So you have a net change in water level rising for this tank. Okay, so you understand the dynamic. So if the water level is rising at 20 centimeters per minute, when the height of the water is at 2 meters, find the rate at which water is being pumped into the tank. Okay, so we need to find the rate at which water is pouring into the tank when you have a leakage of 10,000 cubic centimeters per minute. Now, in this problem, since we need to convert everything to the same unit standard, I would suggest using centimeters because you don't want to have to be in a position of converting cubic centimeters to cubic meters. That would involve an additional calculation or two that you don't want to undertake. So take all these measurements in meters and convert them to centimeters. So make this like 600 centimeters here and make this like 400 centimeters here. So make everybody in terms of centimeters, and the time index will be in terms of minutes. Okay, so that's how we'll express the solution at which water is being pumped in. So we're trying to find so many cubic centimeters per minute. So R will be in cubic centimeters per minute. So the way we proceed is, okay, so we're chasing C right here. C is the rate at which water is pumped in. And so now we have, so if water is pumped in, the rate at which water is pumped in, water is being pumped in terms of a volume. Okay, so we have so many cubic meters of material being dumped in. Okay, so maybe I should annotate here. C is the volume rate. Volume rate at which water is being pumped in, and we'll say in cubic centimeters per minute. So you're introducing cubic centimeters, C cubic centimeters per minute inflow into this tank. All right, so now the change in the volume of the water with respect to time is your inflow, which is C, minus your outflow, which is 10,000. Okay, so this is your related rate. You have an inflow minus an outflow, and that results in a net change in volume. So the volume of the tank, so here's this formula right here. This is the volume of a right circular cone. It's 1/3 times pi times r squared times h. All right. Okay. So now, so what we're pursuing is something like this. We want the change in volume with respect to time. Okay. Yeah, here we go. Yeah, so we've got it right here. So now the change in volume. So if you observe, perhaps I should scroll down. Let me extend the page. There's an omission here. So we have volume of the tank is 1/3 pi times r cubed h. Okay, and this can be considered the volume of the amount of water. So volume of the water, we'll call this volume of water in the tank. All right. So the water starts filling at certain levels, and so the volume would be expressed in terms of the radius and the height of the water. So h, of course, is the height of the water, and r would be the cross section of the water surface. Okay, so h is equal to the height or the depth of the water. Okay, you can consider it as a depth. And then r is the radius of the cross section. And that's a circular cross section. Cross section of water surface. Okay? All right, so now we know that the change in the volume of the water is with respect to time. So what is that? So we have two variables. Now, obviously, as the elevation of the water, the depth of the water increases, r and h are changing with respect to time. So now we have the change in volume. We have to use the product rule for differentiation to compute the change in volume with respect to time. So change in volume with respect to time would equal to pi-thirds, that's a constant, okay, times r squared times the change in height with respect to time plus 3, no, that's not r squared, that's 3r, right? R cubed, I'm sorry. That would be r cubed. Sorry, I was thinking of a cylinder. This is a cone. That would be r cubed times dh over dt plus 3r squared times the change in the radius of the surface of the water times h. Okay, so note the chain rule. Okay, when I differentiated r with respect to t, I had to invoke the chain rule. Okay, all right, so there's your formula for the change in volume with respect to time, and of course, that is equal to c minus 10,000, and we're in cubic centimeters per minute. All right, so now we have a dilemma, right? We have an equation, one equation, okay, well, at least insofar as the left-hand side of this equation goes, the left-hand side of the equation has two variables, r and h. And so, as stated at the outset of this section, we need to replace one of the variables with its representation in the other variable. In other words, we need to find an expression h as a function of r. So if we can express h as a function of r, then we can replace it here, and then the left-hand side of the equation is only in terms of one variable. Okay, and we'll obviously be able to solve for r. So let's see where that takes us. Okay, now there's a thing from geometry called similar triangles. Okay, this is a right circular cone, and it opens up the fact that we can use a concept from geometry that you probably have forgotten. But in similar triangles, you see this triangle that I'm describing right here? It goes from the apex of the cone to the base of the cone, of the inverted cone. So this is a right triangle, what I've just outlined in black. All right, and we know that the height of that right triangle is 600 centimeters, and its radius, or the base length of this right triangle, is 200 centimeters. But now, in this case, let's let this element right here be the surface of the water in the tank, okay? And it's a circle. The cross-section is a circle, and it has, we'll let R be the radius of the circular cross-section, and we'll let H be the height or the depth of the water for this water element, okay? And so now by similar triangles, we have this relationship, okay, right here. Using this formula that I'm accentuating in the blue box, we have R is to 200 that is, as H is to 600. So we can dispense with the big numbers for now and just say, supposing R and H were in meters, we would say R is to 2 as H is to 6. And now we have a formula for R in terms of H. So by similar triangles, okay, it went like this. Okay, so we had a right triangle, like here, and then we had another right triangle. Okay, and so by triangle similarity, these two sides, the ratio of these two, the length of these two sides is equal to the ratio of the length of this side to the length of this side. Okay, since they share a common, since the angles are the same. I think it's called the angle comparison from geometry. Okay, so now we have a formula for R in terms of H. So what can we do to that? What can we, okay, so now R is equal to R is equal to H over 3. So now we have a formula. So we have change in volume with respect to time is equal to pi thirds. And we'll replace R with its expression in terms of H. So R cubed now is what? H over 3? Is that what? Yeah, H over 3 cubed. H over 3 cubed times the change in the depth of the water, or the height of the water with respect to time, okay, plus, now R squared is H over 3 squared times, so the change in R with respect to time would be 1/3 times the change in the height of the water with respect to time times H, because, yeah, times H, the height of the water. Okay, and then plus 10,000 is equal to the ingest, the rate at which water is pouring into the tank. So all we need then, so now we have, all we need then to find C is we need H at what time? Let's see. Okay, so we need a value for H, and we need a value for dH over dt. Okay, so we need these two quantities. So let's see where we go to the problem to find them. We need to see where, okay, so we know that the water level is rising at a rate. So this clause right here, you see this clause right here? If the water level is rising, so this tells us that we have the change in H with respect to T. And so that's why I chose to use H instead of R. In other words, I could have replaced H with its expression in R. Okay, had I done that, what would have happened is I have no information in the word problem that tells me the rate of change of the radius of the surface of the water in the tank. Okay, this information forces me to reformulate the problem in terms of H, the H that we've been talking about, because we have a rate of change for H. This is dH over dt. Okay, so that's why I opted to use H. I should have explained that earlier on when I was when I was making these variable substitutions, but why I chose to use h instead of r. In other words, write this formula in terms of h rather than r, because I have, in the wording of the problem, the change in h with respect to t is 20 centimeters per minute. Okay, and when dh over dt is 20, h is 200 centimeters. Okay, so I can make those, I can plug those in. So when dh over dt is 20, h is 200. Okay, so now just plug it in here, plug 20 in here, and plug 20 in here, and plug in 200 here, and plug in 200 here. Okay, and then go ahead and do the calculations. You know, multiply and add all these numbers up, and what happens is you'll get a value of, let's see here, make sure that we're correct here. Yeah. So we'll get a value for C when you use your calculator to crunch the numbers will be 289,253 cubic centimeters per minute. Okay. So that's how you solve this problem. Okay. The trick is, the strategy is knowing whether to formulate this dV over dt in terms of r or in terms of h. And this statement right here that I've got circled tells you to use h. Okay. Now here, as an alternative method, perhaps it may be easier, but this method that right here, all of this, which is in the online paper-based lecture notes, doesn't really explain this derivation that we went through, and it doesn't explain why you use h as opposed to r. So hopefully this will tell you why you use one variable over another variable. So that's the tricky part, which variable to select and which variable to eliminate. We eliminated r in this problem, and you can see why. Okay, so that was 23. We can work another one. Let's see which one this one be. Okay, how about number 16 of the same section? So next page. I'm running a little bit short on time, so forgive me as I have to paste these in. Let's see how this works out. Toward the end here. Yeah. All right, so print screen, let's see, print screen, and then new, don't save, paste. So number 16, I think it's another similar triangle problem example. All right, so in this problem, we have a spotlight on the ground. Okay, so we've got a spotlight on the ground. Let's see, that would be, say, right here. Shines on a wall 12 meters away. So here's the wall, right here. So the light beam is shining on the wall. And so a man 2 meters tall, so here's the guy right here. Make a little stick figure, right? And he's 2 meters tall, okay. Walks away from the spotlight toward the wall at a speed of 1.6 meters per second. So he's walking in this direction at 1.6 meters per second. Okay, so how fast is the length of his shadow on the building decreasing when he is 4 meters from the building? Okay, all right. So, okay, so here's how we'll deal with it. So evidently, as the guy walks toward the wall, the length of his shadow would be in terms of y. Okay, so as he gets closer, then the shadow will be, this will be the length of his shadow. And he gets, say if he's right here, and if he's right here, then say the length of the shadow may decrease further down to here. So you can see from the physics standpoint, as it gets closer and closer to the wall, the shadow gets smaller and smaller. Okay, so the way we model this problem is we say, okay, well, we've drawn the triangle, okay, the spotlight, the instantaneous position of the guy walking toward the wall. This is right here, this point right here. So the guy is, say, X meters from the spotlight. Here's the spotlight. The guy starts out X meters from the spotlight. That would be his instantaneous position. So this is the instantaneous position, 2 meters tall. All right, and the spotlight hits his head, reflects off the wall. And so as he gets closer and closer, then you'll see the shadow go like this. So Y is equal to the height of the shadow with time. Okay, so now we have X and Y. We have distance from the spotlight, and Y is the height. So we have two variables, one of which we're going to have to eliminate. So we know the guy is walking toward the building in the positive X direction. So his change in position with respect to time is 1.6. Now we need to say, okay, so we need to formulate the height of the shadow in terms of the position the guy is from the spotlight. So we say that X is position, or actually not position, distance from spotlight. Okay, so we need to formulate, say, Y, and so actually, and of course, before we do that, X is a function of t, so we need to say that as well. X is changing with respect to time t. It's a dynamic variable. Okay, so because the reason why I write X of t is because we may have to use the chain rule here. And so we need to express Y of t in terms of X of t, because why? Y of t changes as X of t changes, right? If X of t doesn't change, then Y of t does not change. Okay, and the way we deal with that is we use similar triangles. Okay, and so here we have, so by similar triangles, as you can see in this illustration, when the guy is X distance from the spotlight, 2 meters tall, okay? And when you're 12 meters from the spotlight, when you're at the wall, okay, so at the instant the guy is X meters from the spotlight, okay, his shadow height is Y, okay? And so we have Y is to 12, okay? Y is to 12 because the distance from the spotlight to the wall is 12, as 2 is to X, okay? So that shakes out from the similar triangle notion. And so that's depicted here in this equation. And so now we have Y as a function of X, okay? And so now, as we stated, as the guy walks toward the wall, the height of the shadow changes. Knowing that Y and X are functions of time, we have the change in Y with respect to t is equal to the change with respect to t of this function 24 over x, which is a hyperbola, by the way. Okay, so it's a hyperbolic function. And so when we differentiate this with respect to t, this would be, we have to use a chain rule now. This would be 24 minus 24 over x of t squared times dx, the change in position with respect to time, okay, which we know to be 1.6 meters per second. Okay, so that's 1.6. So all we need now is a value for x of t. Okay, so how do we calculate x? Is there a way? Okay, so when the guy is 4 meters from the building, okay, so he's 8 meters from the spotlight. So we have x being the distance from the spotlight. Okay, x is the distance from the spotlight. So if he's 4 meters from the wall, then he's 8 meters from the spotlight. So we wire in 8 there. And so when we solve for dy over dt, we get this number right here. Okay, so you can use your calculator to verify that. So it's the negative sign is fortuitous, right? Because the negative sign means that it's decreasing. It's decreasing with time. So the shadow is decreasing at a rate of 0.6 meters per second. Okay, and then when he hits the wall, then there's no shadow, evidently. Okay, interesting problem. All right, so what else can we work on here? Another word problem. So we've done things. Okay, so here's one that I pulled from WebAssign, and it's also in the book. This would be problem number 38 in the text. So let's give this one a go. 38 in the text. So I will copy that into the whiteboard from the lecture notes. .38 in the text, problem number 38, section 3.9 of the text. Okay, and so we have this. Okay, so we have two carts, A and B, that I've shown in this illustration, and it's also shown in the book. And they're connected by a rope, which is 39 feet long. Okay, so we have this rope 39 feet long that connects the two carts. And it passes over a pulley. And the point Q is on the floor 12 feet beneath P between the two carts. So yeah, so basically Q is the end point of a perpendicular drop from P to the floor. And so we have cart A being pulled away from Q, point Q, at a speed of 2 feet per second. So cart A is pulling in this direction at 2 feet per second. Okay. So when that happens, of course, the rope will tug on cart B, and so cart B will subsequently move toward point Q. All right, so how fast is B moving toward point Q at the instant in time when A is 5 feet from Q? So if we're 5 feet from Q, how fast is cart B moving toward point Q? All right, so that's the problem. So how do we walk it? So the way, and I've got it parameterized, okay, so I say let's let x equal the distance, so I'll write it here. X is equal to the distance cart A is from Q. Okay. Now, what I'll do is I'll superimpose a coordinate system. All right. And so point Q will be an origin. So that means if I move in this direction, okay, my velocity will be negative because the change in x with respect to time moving to the left makes x's, all my positions, negative with respect to point Q. So moving to the left negates the quantities. If I move to the right, they would all be positive quantities with respect to this coordinate system that I've outlined in red. Okay, so now x is the distance the cart A is from Q, and then in the illustration I also show that y, not to be confused with the coordinate axes, okay, these are just distances. So y is a distance These are variables, not coordinate axes, okay? Distance cart B is from Q. Okay, so we have these results. So we want to find the change in y with respect to time. In other words, the velocity of cart B when x is equal to -5, based on our coordinate system. Okay, so how do we do that? Okay, well, it looks like, looking at the illustration, it looks like we've got two right triangles that we can work with. So we see that x squared plus 12 squared is equal to, okay, well, the length of the rope. Let's consider the length of the rope. The length of the rope is the sum of the lengths of two hypotenuses, right? Hypotenuse? Hypotenuse? I don't know. Okay. Here you have one hypotenuse, and here you have another hypotenuse. And so x squared plus 12 squared is the length of this hypotenuse, and y squared plus 12 squared is the length of the second hypotenuse. And then the sum of the two hypotenuses is just the length of the rope, which is 39. So we can, right off, we have a formula. So the sum of the length of the first hypotenuse is the square root of x squared plus 12 squared. Okay, that's the hypotenuse connecting cart A with point P. Okay, and then the second hypotenuse is the length of the rope. The second hypotenuse is the hypotenuse connecting cart B with point P, the pulley. And so the length of that hypotenuse is y squared plus 12 squared. And then the sum of the lengths of the two hypotenuses is equal to the length of the rope, which is 39. Okay, now we need dy over dt. We also have dx over dt. dx over dt is -2 feet per second. Okay, so we have dx over dt is equal to -2 feet per second, and we want to find dy over dt when x is -5 feet. So we're given that x is equal to -5. So when x is -5, okay, turns out that if we plug in -5 here and solve for y, so when x is, so I won't go through the algebraic calculations, but when x equals -5, we can solve for y. Okay, so y would equal to let's see here. Obviously, y is going to be positive, right, because it's to the right of the origin. So y, well, let's see here. I guess I'll go and step through the algebra. Okay, so we have, so if I plug in -5 for x, we'll have 25 plus 144 plus the square root of y squared plus 144 is equal to 39. And this number right here is 169, and the square root of 169 is 13. So this would be 13 plus the square root of y squared plus 144 is equal to 39. Okay, so the square root of y squared plus 144 is equal to 26. Now I square both sides, and so what is 26 squared? Let me get my calculator. Okay, so 26 squared is 676. So I have y squared is equal to 676 minus 144, which is equal to 532. And so y is equal to the square root of 532, which is 23.065 feet. So we take the positive value because we assume that the cart is to the right of the origin. Okay, so now when x is -5, when x is 5 feet from Q, y is 23.065 feet from Q. Okay, and those are the instantaneous values. All right, so now let's go back to our equation. Let's take, let me see if I can copy and paste. So let me see, select. So let's select this. And let's see, Control C, paste. All right, so there's our equation. And now all we have to do is differentiate with respect to t, because we want the change in y with respect to t. So in doing so, we'll obviously have to use the chain rule and whatnot. So the change, so differentiating this term with respect to t, I'll get x over the square root of x squared plus 144 times the change in x with respect to t. Remember, I'm just using the power rule for differentiation. 1/2 times, okay, I'll be more explicit. So differentiating both sides with respect to t, I'll have 1/2 times x squared plus 144 times to the negative 1/2. That's the power rule. Now I have to use the chain rule. So take the derivative of the content inside of parentheses. That would be 2x times dx over dt. And now differentiate the next term, this term right here, with respect to t. So I'll have 1/2 times y squared plus 144 to the negative 1/2 times 2y times dy over dt. And of course, the right-hand side becomes 0 because the derivative of a constant with respect to time is 0. All right, so now what do we have here? All right, so we have this expression, and so we can solve for dy over dt. So dy over dt, so now we solve algebraically for dy over dt. Let's see, we have some cancellations going on here. That cancels, and that cancels. So we have dy over dt is equal to negative x dx over dt divided by the square root of x squared plus 144. So if we bring this term over to the right-hand side, and then we have to divide all of that, right? Divide that by y, divide it by the square root of y squared plus 144. Okay, so that's the formula for dy over dt when solving algebraically for this term right here. Here's your formula. Okay, and so now x is negative 5. So you have to plug in negative 5 for x. So it'll be minus 5. dx over dt is negative 2 feet per second. Okay, that's x is negative 5 there. And y we said was 23.065. So 23.065 there. And then we plug in 23.065 here. And so when you use your calculator, the number you should get is dy over dt is equal to, hopefully, negative 0.87 feet per second. Okay, so that's what I get. Okay, so that's the cart problem. So I'm hoping you can recognize early on how to replace y with its expression in x, or to solve for y and to solve for, we solve for y, count a value of y based on knowledge of what x is. Okay, and how to instill a coordinate frame and make the signs correct, the negatives and positive signs correct. All right, so another problem. Let's see here. This would be number 28. So let's try number 28. So let me paste it in from the lecture notes. All right. Okay, so in this case, we have a kite 100 feet above the ground. So here's your kite, right here in blue, 100 feet above the ground, and it moves horizontally at a speed of 8 feet per second. So it's moving in this direction, perhaps, at 8 feet per second. Okay, at what rate is the angle between the string and the horizontal decreasing when 200 feet of string has been let out? Okay, all right, so you want to find the rate of change of this angle. So here we have the kite is obviously tethered to the ground or some person, okay? And so this is the string right here. And at the moment it's 100 feet above the ground, it's at it forms an angle theta. This is the angle formed between the string and the ground, theta, okay? And we want to find the change in theta with respect to t, okay? That's the rate at which the angle between the string and the horizontal is decreasing. Okay, and when, okay, so we want to find d theta over dt when the string length is 200 feet. Okay? And we know the height of the kite is 100 feet, and that stays constant. And we know we also are given that the change in x. So if we let x be the distance the kite is, okay, so let me write that down. X is equal to the horizontal distance kite is from person holding the string. Kite is from tether point. We'll call it tether point. Okay. This will be the tether point right here. Okay. So we're given that what? So the length of the string is 200. Okay. So the kite is moving at 8 feet per second from the tether point, so we have this information right here. So the change in x with respect to t is 8. Since we let the tether point define our coordinate system, so anything moving in this direction will have a positive velocity. Okay? And we also know that the cotangent of theta would equal to x over 100. So we can solve for the instantaneous value of x. So x is equal to 100 cotangent theta. We don't know what x is, right? Or we can find the instantaneous value of x, knowing that y is 200 and this distance is 100, so we can do that. But anyhow, since x is equal to 100 cotangent theta, we have the change in position with respect to time, which is equal to 8. Well, we have it. We can also relate the change in position of x with respect to time in terms of theta. Okay, and so that's this formula right here. So that would be 100 times the derivative of the cotangent function. So that would be negative cosecant squared theta times the change in theta with respect to time. Okay, and that's the quantity we want. We want d theta over dt. So we've related, the related rates aspect of this problem is framed in terms of the fact that as x changes, theta changes. And so we've related the change in x with the change in theta in this equation right here, which is, for all intents and purposes, a differential equation. Okay, so now we can solve for d theta over dt. So the change in theta with respect to time is equal to 8. Okay, dx over dt is 8. So that would be 8 over 100. Okay, times 1 over the cosecant squared of theta, which would be negative cosecant squared of theta. So 1 over cosecant squared of theta would be sine squared of theta. Okay, and that would be a minus sign. So, so what is theta? Okay, so we have that. All right. So now it turns out when y is 200, okay, so if y is equal to 200, the sine of theta is equal to opposite over hypotenuse, which is a half, okay? And so, oh, I'm sorry, I forgot. D theta over dt. No, I'm sorry, that's correct. Yeah, I don't need to write that. Oh, I've already solved. No, never mind, scratch that. Okay, yeah, scratch that. Don't paint it, scratch it. Okay, so, all right. Okay, so we want to know what? When y is 200 feet, what is d theta over dt? Okay, so when y is 200, the sine of theta is equal to a half, as you can see from this illustration. And so all we do is we plug in a half for sine theta, but in this case, sine squared theta would be a quarter, right? So when y is 200, we get a value for theta. So you see how y is related to theta, okay, by the trigonometric relationship. So d theta over dt is equal to negative 8 over 100 times 1/4, because sine squared theta would be a fourth. And so that would be, okay, minus 1 over 50. Okay, and the rate of change is expressed in radians, so that would be radians per second. Okay, so the angle is changing at 1/50th radians per second. All right, so the kite problem. All right, and I want to do one more problem. This is a particularly challenging problem. I want to do problem number 26. It's another water tank problem, not a swimming pool problem. Okay, and so this kind of is illustrative of the most challenging problem that we'll solve in this section. Okay, so the last problem of this section. Let me paste it in from the lecture notes. All right, so in this problem, hang on, let me paste it. Number 26. So here we have a swimming pool that's 20 feet wide, 40 feet long, 3 feet deep at the shallow end, and 9 feet deep at the deepest end, okay? And here's the cross section. So it's 20 feet long, 20 feet wide, and this is the cross section. And that's extracted from the figure. So I presume then that the width means that the 20 feet is going into the page. So, but we're just going to process the cross section for now. Perhaps, yeah, okay. Okay, so the pool is being filled at a rate of 8 cubic feet per minute, 0.8 cubic feet per minute. And so you want to know how fast the water level is rising when the depth at the deepest point of the pool is at 5 feet. Okay, so now the top of the pool, of course, is here. This would be the top of the pool. Okay, and you've got this component, this trapezoidal piece right here. All right, so the cross section of the pool is this trapezoidal section right here. Right here. And the height of the trapezoid, okay, so the trapezoid, what I'm saying is let B, okay, so with this parameter B right here, is the width of the water surface. So you see as water pours in, the surface of the water will expand to a certain width. Okay, so you have this expansion along a certain width right here, like here. So that would be the width of the water surface. All right, so the cross-sectional area of the trapezoid, insofar as water has filled into the pool, will be this formula: B plus 12, 12 being the width at the bottom of the trapezoid, times H. And so H is the height. So B is the width of water in the pool, of water surface, and H is the depth, okay, or height of water. And so the area of the cross-section of the pool is given by this formula. So the volume of water that's in the pool would be the cross-sectional area times the width, okay? And as much as you have a rectangular box, you can find the volume of a box is width times height times length, okay? Where width times height, that's the area of the cross-section times the length. Well, the area of the cross-section times the length, okay, or in this case, the width, okay, the area of the cross-section times the width. This would be the volume of the water that's currently in the pool. Okay, now we have a similar triangle situation that comes about from two right triangles. We have, where was it taken? Let me see what X is. X is, okay, so a similar triangle, it's kind of hard to see, comes from manipulating this triangle right here, okay? And so we have X being this distance and then H being this distance. So X is to H as, okay, the base, okay, that distance right there is 6 and this distance right here is 6, okay? So we have X is to H as 6 is to 6. So X is equal to H in this triangle right here of the trapezoid that you can cut out of the trapezoid. And then now we can use similar triangles to calculate a relationship between Y, which is, let's see what Y is. Y is this distance, the width of the water in this particular triangle, okay? So that would be the width of the water surface in this particular triangle. So, and then H, of course, is the depth of the water in this. Okay, so we have this relationship. Okay, so we've got a drawing that says, okay, 16 is to 6 as Y is to H, and now we have, so we now have both X and Y in terms of H, which is the depth of the water. Okay, so so it turns out that the B value, so remember, B is the width of the water surface in the pool. Okay, width of the water surface in the pool, it's equal to X, which is this distance, plus 12, which is this distance, plus Y, which is this distance. But now we reformulated X and Y in terms of H. So X is equal to H. We have 12, and Y is equal to 8/3 H. So now we have a formula for B in terms of H. Pretty amazing stuff. B is now a function of H. And we want to find the change in the water height with respect to time. So how do we proceed with that? Knowing what B is, okay, we have a formula for the volume of the water. Okay, So the volume of the water is this formula right here. There's your volume. And so what do? We replace the B parameter in the volume with its expression in H. So you see how that takes place? So the volume of the water in the pool with respect to H, its height, its instantaneous height, is this formula. Okay, that would be 10. See, 20 times a half is 10. So that would be 10 times B plus 12 times H. But we know what B is in terms of H. We extracted that out from similar triangles. So that would be 10 times 12 plus 11H over 3 plus 12 again times H. So I substituted the expression for B in terms of H. Okay, and so simplifying, this would be 240H. Now I'm just doing an algebraic simplification. 240H plus 110 H squared over 3. So this is the volume in terms of H. And now we know from the information given that the pool is being filled at a rate of 8 cubic feet per minute. Okay? So the change in volume with respect to time is equal to 0.8. And we want dH over dt. So that would equal to 240 times dH over dt. And now the second term will have to use the chain rule. That would be 110 over 3 times 2h times dH over dt. Okay, so, and we're given h, right? The initial value of h. So the depth at the deepest point is 5 feet. So how fast is the water level rising when the depth is, at the point in time when depth is 5? So we know this is 5. We take h to be 5, the instantaneous value of h. So 0.8 is equal to dH over dt times 240 plus 10, 1100 over 3. Yeah, plus 1100 over 3. Okay, and when you solve for dH over dt, you'll get if I did that right, dH over dt is equal to 0.00132 feet per minute. A very slow rate of rise. Okay. All right, so that's how you solve that problem. Okay, so that's pretty much a cross-section of the problems that we'll be working with in section 3.9. There's quite a few more word problems. I've got some additional ones posted on the website. Let me see here. There's one in particular that I would like for you to take a look at. Let me check it out on the class website. Or for that. Let me see if it's still there. If not, don't. I won't have you worry about it. I think this one shows up in WebAssign. Let's see. I'm checking. So let's see. I'm checking. 1 second. Bear with me while I check. This would be HW12. oops, not HW12, maybe HW13. Yeah, go to the class website, and in the section previous homework assignments, I would like for you to look at, let me see, at question number 6. Okay, I have the solution to question number 6, which corresponds to question number 14 in your text. Okay, so the solution to question 14 in the text of section 3.9 is the same as question number 6 of homework 13 on the previous homework assignments posted on the class website. So it has to deal with a ship. A is 150 kilometers west of ship B, blah, blah, blah. Okay, so question number 14 in the text corresponds to homework number 13 in the previous homework assignment section on the class website. That would be homework number 13, problem number 6. So I want you to take a look at that solution, because I think that was one that last semester students had the most trouble with in WebAssign. So look at the details of that. It's another related rates problem. It doesn't involve having to use the law of cosines, I don't think, but nevertheless, take a look at it, as well as all the other problems in homework number 13. You'll have much more practice there. I pretty much worked all of the problems of this section for you. Okay, so that concludes the lecture for section 3.9. I'm hoping that you're well along in your WebAssign development. Also, I can say that with this, you should have all of the tools now to do your project number 3, which will be due on the Thursday, or it'll be due, I guess, round about the time you take your exam for 3.2. So please, at this time, start getting begin work on the project for Chapter 3. And as usual, contact me if you have any questions. All right, so that's it for this lecture. Take care.